everyone. We are looking into geophysical methods of logging. Toward the end of the last lecture, we had a look into fluid conductivity log. In fluid conductivity log, we are going to measure the electrical conductivity of the fluid in the borehole. That means this is the borehole. The borehole is filled with the drilling fluid. This is the ground surface. And we are going to just lower a conductivity probe that will measure the variation in the specific conductance of water with respect to depth. This is depth, this is the conductance. It is also called as electrical conductance. Usually the unit is microsiemens per centimeter, and we will just measure the variation in the electrical conductivity below the surface or conductivity of the borehole fluid. What are all the information it can give? The abrupt change in the conductivity value is due to external fluid mixing with the borehole. This is the borehole we have drawn, right? This is the borehole. Right over here, the conductivity is increasing. Probably the external flux, groundwater flux is much more here. The water is comparatively having a different water quality. That means conductivity increases at this particular depth, probably indicating influx of saline water into the borehole. It cannot completely invade, it dilutes the mud. So this is how the variation in electrical conductivity of the fluid within the borehole is measured. That helps us to understand quickly whether there is any interaction between the borehole fluid and the surrounding formation water. Similarly, at some location there is a decrease in the electrical conductivity. So this is the general electrical conductivity of the drilling fluid. Over here there is a decrease in the conductivity. Possibly here too there may be a flux of groundwater where groundwater is comparatively fresh, due to which conductivity has reduced. So electrical conductivity of the fluid is a measure of total dissolved solids. Water will become very good conductor when it has got more salinity. A fresh drinking water will have comparatively higher, the fresh groundwater will have comparatively higher conductivity. With reference to that, saline water will have much more conducting capacity, due to which this, if you consider this is the fresh water and this is much more fresher, that means salinity is very less, more or less a pure drinking water, whereas here the groundwater is very much contaminated, leading to high conductivity, right? So this is how we are able to understand between the we are able to understand the interaction between the borehole fluid and the surrounding fluids. That is the application of the electrical conductivity log or fluid conductivity log. That means we are able to understand about the quality of groundwater around the borehole. That means we are also able to delineate zones where there is fluid movement into or out of the borehole. Right, at some location there can be some leakage. Borehole fluid may be continuously leaking. That can also be identified using the conductivity log. However, the electrical conductivity also depend on the temperature of the fluid. That is why we had seen previously temperature logging. Always resistivity has to be corrected for, or in other words, resistivity or conductivity of the fluid has to be corrected for the temperature. Hence, we have already taken the temperature log. Temperature log also has to be correlated with the conductivity log. If the temperature variation is significant, we need to apply a correction factor to arrive at the correct conductivity of the fluid. So these are the two major applications of conductivity log. More or less the applications are similar to that of temperature logging. Right. And the next is nuclear magnetic resonance logging. Already we had seen SNMR, which is surface nuclear magnetic resonance. We had seen already its application. Here, in the same technique is also used in the borehole. So, NMR technique measures the magnetic signal emitted by spinning protons. Right. So, when we are talking about spinning protons, the NMR mostly focuses into the detection of hydrogen nucleus. Right. So, what is the significance of hydrogen nuclei? So, hydrogen nuclei have protons of interest, especially in NMR logging. Because of the reason, the protons of hydrogen returns to their original states. Right? It returned to its original state following the excitation or simulation by the magnetic field, which means we are going to make use of a strong magnet to simulate the hydrogen nuclei, especially the protons in the hydrogen. The speciality of this hydrogen protons in hydrogen nuclei is when they are excited with the help of a strong magnet, they get excited, and after you stop the application of the magnetic field, they return back to their original state. Right? When they are returning back to the original state, they produce some energy. That frequency or radio frequency energy is also measured. Right? So these signals, which are measured as parallel and perpendicular to the direction of the applied magnetic field, and the measured signals are expressed as time constants. Right? That means the time it takes, or the time constants, are related to the decay of magnetization of the total system. As the protons in hydrogen nuclei are excited and they align themselves in a particular direction, after these signals are stopped, they return back to their original state, and the way in which they are returning back is measured, which is measured in terms of time constants. So time constants are related to the decay of magnetic field with reference to the direction, especially with reference to the perpendicular or parallel direction. And as we have seen, this method, we are able to understand the response of hydrogen atoms, right, to the magnetic field perturbations, and this is exactly similar to the magnetic resonance imaging which we all undergo. Sometimes we are also undergoing magnetic resonance imaging, wherein the image is able to clearly pinpoint the issues with regard to the tissues binding the bones, especially when we have some issue with regard to our spine or back pain. Sometimes the doctor advises to undergo magnetic resonance imaging. Using that image, we are able to understand the strained tissue, right, or whether the tissue has bulged out at a particular place. So we are able to understand that. The same technique is also used here, since the protons in hydrogen atoms return back to its original state after the excitation. It is of greater interest to us. That is the greatest application of NMR. That means we are able to pinpoint the locations where we have hydrogen atoms beneath the surface of the beneath the surface of the earth. The geological formations, there is no scope for presence of hydrogen. only possibility is presence of hydrogen in water as well as in hydrocarbon present in the pores of the subsurface formation. So using this technique, we are able to pinpoint the presence of water and oil. So previously, right, this method was only used in oil industry because this method was very expensive. Since 1960, we are using this. But however, the recent NMR tools are made very cost effective, right? And because of that, it is easily used to acquire high resolution hydrogeologic parameter estimation for even for shallow boreholes and also for aquifer investigations, right? However, they were previously focused mostly in oil industry to understand the variation at greater depth. But today it has become much more common. There are many companies who own NMR, especially in developed countries, right, which can be hired to understand about the variation in hydrogeological parameters at a comparatively higher resolution. So, nuclear magnetic resonance provides estimates of total porosity because of the fact which we had discussed just now. Since hydrogen is excited by this technique, right, with the help of a strong magnet is lowered in the sonde which excites the hydrogen ion, and this technique can also be varied, right, by focusing the energy of magnetization to shallow region to greater distance from the borehole. Thereby we are able to overcome the effect of the disturbed zone, that is the invaded zone, that is the mud invaded zone, and beyond the mud invaded zone we are able to sense the formation characteristics. Due to this reason, due to the reason of due to the reason that our focus is on the hydrogen atoms, because the protons in hydrogen atoms alone gets excited, returns back, spins back to its original position, emitting some signal which is sensed. So we are able to get an overall idea of the total porosity of the formation. With the help of the porosity, we can understand about the pore size distribution. From porosity, we can also arrive at permeability. Porosity and permeability are reasonably related. Right? Very fine the pore size, the permeability will be very less. When the size of the pores are larger, permeability will increase. Right? So using some algorithm, right, some empirical relation from porosity, we can derive the permeability of the formation. Further, as we had seen under radioactive logging methods as well as in resistivity logging method, we can also determine how much of the pore fluid is saturated with oil, how much of it is with water. To some extent, we will be able to differentiate by comparing the signals in the zone which is having only water and also by comparing the signal which we have received from the unsaturated zone. Unsaturated zone is the zone above the water table where the pores are filled partly by the water. Using this signal, we will be able to also understand the saturation with respect to oil and water. And the advantage is, since it is easy to operate, we can get the continuous high resolution data throughout the borehole, throughout the length of our logging. And the data acquired, as I told you, is from multiple narrow bands of soil matrix at various radius from the center of the NMR logging tool. That means we are scanning the circle around the NMR tool. So due to which this method allows to understand about the conditions beyond the invaded zone. That is, disturbed zone is the mud invade. During drilling, we had used mud. Drilling mud, we are able to understand beyond the mud invaded or disturbed zone around the borehole can be assessed. So NMR's vertical resolution, however, is little bit limited compared to the other borehole geophysical logging methods, right? And still it is not very less. Approximately the vertical resolution is about half a meter, right? Half a meter will be the vertical resolution. And another limitation is this method is a little bit slower, right? Because we have to excite the formation around the borehole with the strong magnet by creating strong magnetic field in the sonde, right? So it takes some additional time, but still it is not very slow. Still the logging rate of about 15 meters per hour is possible using this method. And coming to the interpretation, right, what we are going to do is we are actually energizing the protons in the hydrogen nucleus. These protons previously are aligned in different directions, but when a strong magnetic field is emitted, this magnetic field makes these protons to align in a particular direction. As and when we stop the application of magnetic field, the realignment to its original position creates some signal which is measured. This is known as like transverse relaxation time. That is what we are measuring. So it is the transverse relaxation time. The integration of the relaxation time actually gives the total water content, and distribution along the axis is indicating the water that is in mobile form, right? That means bounded water and the water in mobile form can be distinguished by this method, right? So here the first image shows this transverse relaxation time, right? Based on the tools provided, especially the software tools provided by the manufacturers, we will be able to segregate from the T2, that means the transverse relaxation time, we will be able to arrive at the bounded water, immobile water as well as mobile water, right? So when you deploy the log in the unsaturated zone, the total water content in the unsaturated zone reflects to residual water saturation. That means like soil water retention or simply specific retention. Specific retention is the ratio of the volume of water retained to its total volume. So when you deploy the tool in the unsaturated zone, it is able to come out with the specific retention if it is a dry period of time, right? So we are able to get the residual water saturation. Whereas when the tool is lowered into the saturated zone, it is able to give us the total water content. So total water content helps us to determine the total porosity of the formation, right? So intervals with high mobile water. So we are able to differentiate the mobile water based on the relaxation time. So a high percentage of mobile water indicates what? When the movable water is very high, indicate the zone has got high permeability, isn't it? So here in this diagram, if you look at these green colors, right, here it is much higher, indicating these zones are highly porous zones because it has got very high amount of mobile water. Whenever we have high permeability, the residual water content will be very, very less. That is bounded water. That means water under retention will be very less when the size of the pores are bigger. When the size of the pores are bigger, obviously it indicates permeability is more. So we are able to differentiate highly permeable formation, which is likely to have comparatively coarser grains, right? Comparatively coarser grains and high percentage of bound water. That means all this pink color, when the percentage of bound water is much higher, they indicate presence of clay zones, right? Very fine grained soils. Only in clay, movable water will be very less. It is obvious, all of us know, isn't it? In the clay, it is difficult to extract the water out of the clay. But still water, large amount of water is present in the clay. Its porosity is about 50%, 45 to 50%, right? That means half of the total volume of clay has water, but water cannot be easily removed. So this bound water indicates finer formation, right? So this is how the nuclear magnetic resonance logging is helping us to understand whether the water in the pores is mobile water or bounded water, and put together we are also able to get the total porosity of the formation. From the porosity, there are different algorithms available. As I had just now mentioned, the porosity can be helpful to determine the hydraulic conductivity as well as the pore size distribution using different tools or algorithms developed and empirically tested on various soils and rock types. That means there are already empirical relations that exist to determine hydraulic conductivity from the porosity, right? There can be some error in that, but nevertheless, these algorithms have been developed nicely, right? We making use of these empirical relations, and they have been tested on various types of soils and rock types and mixture of soils. So from using that tool, we can also estimate the hydraulic conductivity. Here is the such estimate of hydraulic conductivity using different algorithms, right? As we had seen, right, wherever the bound water is more, right, we are going to infer that as clay formation. Obviously, in clay, hydraulic conductivity is less. Here in this zone, right, where the mobile water content is much higher, indicating here the K value is high. High K, here it is low K. So this is how nuclear magnetic resonance logging, with the help of this, we are able to understand the porosity of the formation below the surface of the earth, right? This is only up to 20 meter. Even at 2000 meters, we are able to understand the amount of porosity. Porosity in turn can be also transferred to estimate hydraulic conductivity or the permeability of the formation. These are the applications of nuclear magnetic resonance logging, right? And we had also seen previously under gamma gamma logging, we have estimated the bulk density of the formation. From bulk density, we derived the porosity, right? And under resistivity logging too, we have estimated the porosity of the formation as well as the percentage saturation of the pores with respect to water and oil. So all these three logs can be integrated and compared. That means bulk density estimates from gamma gamma logging. From there we would have estimated porosity. Here also we have estimated the porosity, right? This can be compared with the gamma gamma logging as well as resistivity logging to arrive at a meaningful interpretation about the properties of the rock below the rock and other formation below the surface of the Earth. One thing I didn't mention under the NMR logging. So NMR logging is possible only in the non-metallic cased holes. Uncased holes, certainly NMR can be deployed, and NMR can also be deployed in PVC cased boreholes. However, NMR is not possible in the metal cased pipes because it works on the principle of magnetism, right? So metal casing, in metal cased holes, nuclear magnetic resonance is not possible.